So the mother of all questions dealing with working with trig expressions is the identity, right? Trying to prove that one heinous looking thing with sines, coses, and tans in it are equal to some other heinous thing with sine, coses, and tans. And there are two identities that we're going to use in order to work that out, plus the skills you learned in factoring trig expressions, fancy factoring trig expressions, and common denominator of trig expressions. So with all that stuff put together, we should be able to pull this off. So the two identities that you should have learned about in grade 11, as I wait for my blue marker to work here. Come on. It's been a while. So the first one is that the sine of anything, if you square it, plus the cosine of that same thing, n squared, adds up to exactly 1. So this is one of the Pythagorean identities. And if you want to see why this is true, then scroll down below the video, and there are some notes there, and you can see a geometric justification for that to see why it's true. So what we're doing then is we're trying to show that something like this, sine alpha plus cos alpha squared, is equal to 1, for example. So if you had an expression like this and you were trying to solve it, you might see the square on there and say, I can undo a square with a square root, so that would give me sine alpha plus cos alpha equals plus or minus the square root of 1. And that's fine, but now you've reached this place. I have a sine acting on a function and a cosine acting on a function. And in order to break this, I would need the appropriate antifunction. So I could try and use arcsine to break this, but arcsine does not break an arccos. So you get this all jammed up in there. Try the other way, use an arccos to break this, but it doesn't break a sine. So now I'm going to end up with arccos of sine of alpha, and it's a hot mess. So I'm not going to be able to do this with normal linear algebra techniques. So we're going to have to go into some nonlinear algebra where you start using tricks like this one in order to change this expression, which I can't solve, into something that I can. So if I just erase this here, and we'll try again. The first thing I'm going to do is I'm going to notice that this plus this squared is the same as sine alpha plus cos alpha multiplied by sine alpha plus cos alpha. It's just itself multiplied by itself, and that's supposed to equal 1. Now that looks like something you got from factoring of a trig expression, right? It's a thing plus a thing times a thing plus a thing. So if I FOILed this out, I would get sine alpha times sine alpha, which is sine squared alpha. Sine alpha times cos alpha, which is a sine alpha cos alpha. Cos alpha times sine alpha, which is a cos alpha sine alpha. And a cos times a cos, which is a cos squared. And that's all supposed to equal 1. Okay, I'm going to look at the mess I've made, because it doesn't look like it's better at this point. But I'm going to see that sine times cos and sine times cos are the same thing. So I can add them together. That means there's 2 of them. 2 sine alpha cos alphas. And then I have this thing. And I have this thing. Okay. Now, at this point, you might be looking at it saying, this isn't any easier than that. I used to have 1 sine and 1 cos, and now I have sines and cos all over the place. And that's, some of them are squared, which is even worse. But I will draw your attention to the fact that this thing is one of your Pythagorean identities. So I can replace all this garbage, sine squared alpha plus cos squared alpha, with a 1. So I'm going to do that. 2 sine alpha cos alpha plus 1 equals 1. Okay, well I'm just going to subtract 1 from each side, so I get 2 sine alpha cos alpha equals 0. All right, now in this situation, I have a thing multiplied by a thing equals 0. And that's the perfect setup for cases. So case 1, either 2 sine alpha equals 0, or case 2, cosine alpha equals 0. So I can solve this. Divide both sides by 2, I get sine alpha equals nothing. And so if I arc sine that, that has a few solutions. Sine hits 0 at 0 and at pi plus 2 pi n. And cosine equals 0 at pi over 2 plus 2 pi over n, and at 3 pi over 2. So you'll have to go back and check your sketches of things in order to see that that's the case. I guess I could pop a plus 2 pi n on that. So if you look at what happened, I took something that my linear algebra skills couldn't solve. And so I exploited some of this factoring stuff and this particular identity in order to boil it down into something that I could split into case 1 and case 2, which is a nonlinear algebra technique. And then I rendered it down into solutions. So without this little fact, this thing was unsolvable by our normal methods. But once I throw the trig identities in, then I'm able to get an answer. All right, the second thing that you can do with these trig identities is to take something that's really complicated. Notice I don't have an equal sign, so I'm not trying to solve this. I'm just trying to simplify it. Because I've got this big mess of sines and cosines, and I wonder if I can compact them down into something that's a little tidier. So the first thing I'm going to look at is I'm going to see this sine plus cos squared. Now we did that once before in the example prior and found that sine alpha plus cos alpha squared ended up making sine squared alpha plus cos squared alpha plus 2 sine alpha cos alpha. And all that stuff is over top of this. And I have minus 1 over tan alpha minus 2. Okay, so I'm going to look and see what I've got here. Sine squared and cos squared added together give me 1. So I can replace this structure with a 1. Oh, I shouldn't have done that in pink. Oh well. And then the bottom here is sine alpha cos alpha. Okay. Now I have this thing here, minus 1 over tan alpha minus 2. So this is a little less complicated than that was because there's no square left. So we're going to keep going. If I see a tan in my expression, I'm going to use the other Pythagorean identity, which was tan of a thing is the same as sine of a thing over cos of a thing. And therefore, 1 over tan is, you just flip this fraction, it would be cos of that thing over sine. So I have a 1 over tan here, so I'm going to replace it with this. So I've got 1 plus 2 sine alpha cos alpha over sine alpha cos alpha minus this thing, cos alpha over sine alpha, minus 2. Notice I've left some convenient space there. So I took these things and I've simplified it by getting rid of the square. Then I simplified it by getting rid of the tan. And if I look at that, I've got a fraction with sine and cos in the denominator, a fraction with only sine in the denominator, and a thing that's not a fraction. So if I look back to the common denominator for trig expressions section, I'm going to try and make this have the same denominator as that? If I look, it's got a sine and a cos. This is a sine, so it needs me to introduce a cosine in the bottom and a cosine on top. That's done. Now 2, I could make 2 have the same common denominator as this if I did 2 sine alpha cos alpha over sine alpha cos alpha. So I have 3 fractions, each with the same denominator. So I can combine that into a single fraction. It'd be 1 plus 2 sine alpha cos alpha minus cos squared alpha minus 2 sine alpha cos alpha all over top of this common denominator. Now something a little interesting happens there. I have plus 2 sine alpha cos alpha minus 2 sine alpha cos alpha. Those two things undo each other. So I'm left with 1 minus cos squared over sine alpha cos alpha, which is considerably simpler than what I had up there. Now if you look at this thing, and if I look at this thing, do you notice that if I move the cos squared over to that side, it would say 1 minus cos squared alpha, which is exactly what I have written there? So I can use this identity to replace 1 minus cos squared alpha with sine squared alpha. And I get sine squared alpha over sine alpha cos alpha. Well, a sine on top divides out a sine on bottom, and I'm left with sine alpha over cos alpha, which is the same as tan. So this whole expression up here, this monster ugly thing, if I'm putting in pi over 3 or pi over 4 or some like non-fraction of pi radians into this gross expression, I would get exactly the same answer if I just parked her in tan. I'd get exactly the same numerical value. So that's a lot easier to do. It took some work to get there. But
just letting everybody know we are all clear and custodians can unlock entrances. Thank you.
But if you, I lost my train of thought. So that's a lot, it's a lot of work to get there. But by the time you do, you have this nice, tidy expression that you can replace this honkin' mess with. And that will become very handy when you get to calculus or anything past this point, where this kind of garbage will start showing up in your answers, and you want to be able to distill it down to the simplest possible expression that you can. Okay, so if I have given something like this, right, show that this thing is the same as that thing, presumably because I have this and I'd like to replace it with that, or I have this and I'd like to replace it with that in some larger problem, I need to use this fact and this fact along with factoring, fancy factoring, and common denominators in order to show, like to manipulate one side or the other or both to show that this thing and this thing are equivalent to each other. So what I'm going to do then is I'm going to separate it into what's on the left side and what's on the right side. And I'm going to forget that there's an equal sign at all. So I've got sine alpha, cos alpha over here, and I have tan alpha minus tan alpha sine squared alpha sitting over here. Okay. Now, there's a lot of ways you can go about this. But I want you to try and keep in mind the stuff that you've been doing in this section. So first thing we're going to do is we're going to look for this. And I don't see sine squared plus cos squared anywhere in this. Second thing I'm going to look for is if I've got a sine or a cos over top of each other, and I don't seem to have that. So there's nothing I can do with these right now. Now I'm going to try factoring. That was the first tool that we talked about in this section. So I'm going to look over here. I don't have any adding or subtracting, so there's nothing to factor at all. If I look on this side, I have a thing minus a thing, and they both contain a tan. So I could factor tan alpha out of both of these. So I'm going to do that. Pull the tan alpha out in front. That will leave a 1 here as a placeholder. Subtract sine squared alpha. Okay. Now, how did I know to do that? I didn't. I just looked at this and thought, I can factor tan out, so I'm going to do that. When I do that, I'm left with this thing, which looks like a 1 and a sine squared. That looks a lot like this. If I threw this thing over to that side, it would say 1 minus sine squared alpha equals cos squared alpha. So I'm going to do that because it will make the expression simpler. So that would be cos squared alpha. Okay. So I'm going to look at this, and I'm going to look at this, and I'm going to think about what I've done so far. I used to have a thing subtract a thing on this side, but not on that side. My factoring and my use of the Pythagorean identity reduced it into a thing times a thing, which is what this side is. So I've made progress. They look closer to each other. So what's different about them? Well, this one has sines and coses, and this one has tans and coses. So I don't want tans, I want sines. So I've got to think if there's a way to turn a tan into a sine, and there is. This Pythagorean identity. So instead of tan, I'm going to use this version. Sine alpha over cos alpha times cos squared alpha. Now, how did I know to do that? I didn't. I just looked at what I had. Right? I had a tan and I wanted a sine. So is there any place I can exchange that for? There it is. That's the exchange rate. Dump it in. And you're going to try this about 15 times. And the first 14 are going to make a hot mess on the page. But the 15th time, you're going to spot the thing you need to change, and the whole thing will just fall apart. Like this one's about to, because a cos squared divided by a cos is gone, and I'm left with a single sine and a single cos, which happens to match exactly what I had over there. So I have shown successfully that sine alpha cos alpha is identical to this in value, even though it doesn't look like it at first. So I have a new one. I'm going to try and show that this thing is equal to that thing. So I'm going to take a look at that, and then I'm going to look for tans, and I don't have any tans. This is all sine coses on this side and all sine coses on that side. So fine. I'm also going to look at this side and see that there's only one bracket here, and there's two brackets there. So that's a place that I'm going to start working. I'm going to see if I can turn two brackets into one bracket, or one bracket into two. So here's my left side. Sine alpha cos alpha squared. And over on my right side, I've got this thing. But I'd like you to think about the units that you did prior to this. And I see a thing minus a thing multiplied by a thing plus the thing, right? They're exactly the same bits, but one's negative, one's positive. That is a difference of squares factoring. So if I undid that, I would end up with something that was a little less complicated. So I'm going to do that. Sine times sine gives me a sine squared. A sine times this gives me a positive sine cubed. A sine squared times a sine gives me a negative sine cubed. And a negative sine squared times a positive sine squared gives me a negative sine to the power 4. And just like in all difference of squares factoring, these two things end up undoing each other, and I'm left with sine squared alpha minus sine to the power 4 of alpha. Okay? Well, we're getting there. So I'm going to take this and I'm going to factor out a sine squared, because I can. Right? You see there's signs here and signs there, so if I did that, that would make this a little less complicated. That would leave 1 here, and it would leave negative sine squared here. Okay. Well, again, looking at it, I have a sine and a cos, and I have a sine and no cos, but I have this 1 minus thing here. Well, that thing there, and you're going to start dreaming about 1 minus sine squared, and at 3 in the morning, you're going to sit up screaming cos squared alpha in your sleep. So sorry about that. But if I look at it, it's this thing. It's been rearranged. So the sine squared over there would be 1 minus sine squared. So I'm going to replace this with cos squared. And I get this. And I'm tired of working on the right side, so maybe I'll work on the left side a little bit. A thing times a thing squared means you have to square the first thing and square the second thing, and just accidentally, I've got a match. So by working on the right side a little bit, by undoing some fancy factoring and making one replacement, and then applying some exponent laws to the other side, I've shown that this expression is identical to that expression. Okay, so I'm going to show that tan alpha equals this. All right, so looking at that, I have a thing that's a fraction and two things that are not. So I'm going to try and fix that by introducing some common denominators. But before I do that, I'm going to get rid of all of those tans so that there's no tans at all. It's just combinations of sine and cos. That's a good habit to get in. Most cases, that makes it easier to do. So my left side then, if I replace tan with this, I get sine alpha over cos alpha. And on my right side, this tan alpha becomes a sine alpha over cos. But there are two extra powers of cosine in the denominator, so that makes this a cos cubed. This one here, tan is sine over cos, and the whole thing is cubed. Or I can write that by cubing the numerator and the denominator, like so. And so if you look at that, this has inadvertently created a common denominator. So I can just combine those two fractions there. So my right side becomes sine alpha minus sine cubed alpha over cos cubed alpha. So you look at that and you think, is there anything I can do here? Well, I see a sine and a sine, so I can factor. I'm going to do that. That leaves a 1 here and a minus sine squared alpha. Imagine that. This thing keeps coming up again and again and again. Throwing that over there gives me 1 minus sine squared alpha, so I can replace it with cos squared alpha. Maybe getting ahead of myself. I should finish one line before I go to the next. So this thing is cos squared alpha. And a cos squared divided by a cos cubed eliminates the ones in the top and leaves only a single power in the denominator, leaving me with sine alpha over cos alpha. Well, there you go. This side happens to match that side. So I've shown that tan alpha is the same as this horrible expression. All right, so we're going to try and use these things in our skills to try and show that this equals that. Now, before I get started, And before you get started, whenever you do one of these, you should take a look at the pieces that are there and maybe imagine how you're going to get there. So I need to turn this mess, which has three separate things, into just a single cosine squared. So let's just look at what's wrong with this. It has tans in it, and it shouldn't. It has sines in it, and it shouldn't. It doesn't have any cosines, which it should. So just starting there, I can see that I need to turn these tans into sine over cos, because I need to not only get rid of these, but introduce factors of cosine. So I'm going to do that first. So my left side, I will just leave as cosine squared. And my right side, I will write 1 plus sine over cos. And it's squared, so they're both squared. Sine squared. And I've got tan here, so it's that sine over cos. And it's squared, so I'm going to square both of these. Okay. So you just sort of stop and reflect on what you've done. I've got cosines and I've got cosines. That's good. I have three things added together here, and there shouldn't be. There should only be a single one. So I try to think about how I can collapse those into a single expression. And if you notice, this has a cosine squared in the denominator, and this has a cosine squared in the denominator, so they can be combined. This one does not, but it could. If I wrote 1 as cos squared over cos squared, I've just accomplished common denominator for all three of those fractions. So I'm going to combine them as one expression. That'll be cos squared alpha plus a sine squared times a sine squared is a sine to the power 4 minus sine squared alpha all over a cos squared alpha. Okay, now what? So it's down to being a single fraction, which is good, but I'm not supposed to have a fraction at all. So somewhere in this mess, I should be able to divide out this cosine squared. And I can do it in the front term, but I can't do it here, and I can't do it there. So somehow I have to conjure out a cosine squared from both of these terms. I'm not really sure how I'm going to do it, but I do see that this is a sine squared and that's a sine 4, so I can factor sine squared out of that. I don't know if that's going to do anything for me, but it's something I can try. So I'm gonna do that. Let's see what I got. So I can take a power of 2, sorry, not cos, out of this, which leaves me sine squared alpha minus 1. Okay. Now, you might look at this and think you can combine them, but you cannot, because this thing has a multiplication happening over here, and Bedma says you have to do that first. So I can't combine those with Pythagorean identity, but I might be able to combine this with that. And so to show you, if I took sine squared and I moved this over, it would be sine squared minus 1, which is what I have sitting here. I'd have to boot that to the other side. That would make it negative cos squared. So this thing here can be replaced by negative cos squared alpha. So what did I accomplish there? Well, I reduced some of my sines and I introduced the cosine into both of these terms. So I can factor it out now. Cos squared alpha. That leaves a 1 here and a negative sine squared alpha here. Cos squared alpha in the bottom. Those two things divide away. And I'm left with 1 minus sine squared alpha, which is that thing that keeps showing up. It's this Pythagorean identity again. It's with the sine squared kicked over here. So 1 minus sine squared would be cos squared. And that is what I was trying to show. So the point here is it's a bit of a wander through the woods. You start with something that's gross, and you look for little telltale signs, right? Like this has tans, this does not, so I'm going to get rid of my tans. This thing has a whole bunch of stuff separated by pluses and minuses, this does not, so I'm going to try and combine them. This has a bunch of signs all over the place, this does not, so I'm going to factor them out. And accidentally, as I went through, I keep getting sine squared minus 1 or 1 minus sine squared, and I can flip-flop back and forth between sines and cos using that thing, if I've got that set up. So this is one of those skills where it will feel impossible until you have that like lightning bolt moment, and then it's really quick. You start seeing the patterns that keep showing up. So you're going to have to just take a deep breath, find your happy space, and give it a go. And if you get stuck on the first one, do not death spiral on it. Get as far as you can, stop, go on to the next one, and then chat with your friends. See how far they got. And between your work and their work, and the next person's work and the next person's work, you might start to see if you made algebra errors. You might start to see if you got negative errors. You might start to see if you have a puzzle piece sitting there that you're just not recognizing until you get in the habit of spotting these little clues and getting to the end. So I wish you luck.